Hello? Hello? Oh, that sounds pretty good. Oh, but it's doing the looping thing again. Oh, that sounds pretty good. Let's do a plosive test thing again. Oh, that sounds pretty good. Let's do a plosive test thing again. Oh, that sounds pretty good. That's terrible. Let's do a plosive test thing again. Oh, that sounds pretty good. That's terrible. Let's do a plosive test thing again. Oh, that sounds pretty good.
What if I do this?
That's terrible. Let's
better
do a
now?
plosive testing again. Oh, that sounds
horrific.
pretty good.
What if I do this?
That's terrible. Let's
better
do a
now?
plosive
horrific.
testing again. Oh, that
that's
sounds pretty good.
What
Plosive test.
if I do this?
That's terrible.
Let's.
Plosive test.
What if I do this?
That's terrible.
Let's.
Plosive test. That's terrible.
Let's.
Plosive test.
I mean, I guess it's better if I leave it
terrible.
like that.
Plosive test.
I mean, I guess it's better if I leave it
terrible.
like that.
Plosive test.
Okay. I appear to be live and have viewers. Well, maybe I have viewers. Can you hear me? Am I hearable? Can I be heard? No one's typing, so that seems to be a bad sign. Oh, never mind. I can be heard. Wonderful. Okay. Excuse me while I pull up my notes, which I have definitely written. A bit of echo. Oh no. What does that mean? Is it better now? No. Oh gosh. Oh, okay. Okay, wonderful. I'll just leave it to you to figure out where the echo is coming from. Okay, I'll give people a few more minutes to join in while I get a few things set up. So the unfortunate reality of the situation is that I don't have any more Asian takeaway stories because I haven't been doing takeout. I've been cooking. I've been making myself fajitas. Although my friend tells me that I'm actually making quesadillas, but I don't really know what the difference is, so I'm just going to continue to call them fajitas. Turns out cooking is pretty easy. If you just put things into a pan and make the pan hot, then you get food that is edible. One thing I have been going out to buy is there's this really nice dessert place around the corner. They do these cakes. They have like these massive cakes, and you buy the cake by weight. So you ask for 100 grams of cake. They cut out like a section of the cake and they put it in a bag for you, and you buy it. So the first time I went there, I was like, this Oreo cheesecake looks really good. So, I'd like 100 grams of that. They said okay. So they cut out a slice. They put on the scale machine. And they say, oh, this piece is actually 120 grams. Is that okay? I was like, sure, that's fine. It's just a bit of extra cake. And so it cost me a bit more than I thought it would. I thought that was just a one-off thing, but actually every single time I've gone back there, they always consistently give me slightly more than I asked for. I always ask for 100 grams of some cake, and I always get a little bit more than that. It's like 110 grams, 150 grams. Okay, that's a lot, but they keep giving me more cake. And at this point, I have to think it's kind of intentional. I've been thinking of just going in there and asking for less cake than I actually want, so that they'll upsell me the amount of cake that I actually intended to buy in the first place. It's kind of like the opposite of those coffee shop things where, every time you buy a coffee, you get a stamp and your 11th coffee is free or whatever. It's like the opposite thing when I go to this cake place. Every time I go in and buy 10 cakes, I actually buy 11 cakes. Okay, I think that's enough time. So I'm just going to get straight into the lecture. Okay. Persistent secondaries. I've just realized that this microphone makes it so you can kind of hear me making non-speaking sounds like breathing and swallowing and stuff like that. Unfortunately, there's not much I can do about it because my microphone setup is like, I have a desk microphone, but it's really weak. So I have to tuck it into the collar of my shirt, which means it really amplifies all the sounds that come from my chest. So you're just gonna have to live with that, I'm sorry. I have figured out that pointing the microphone away from my mouth, even though it makes the sound a bit weaker, it stops the plosive sounds from like being really jarring. At least I think so anyway. Oh, I could join the voice chat. Hello?
Hey!
Hi. Can you hear your own voices on the stream?
Hey! Oh Jesus! This is very loud. Oh no! Okay, I've muted the stream.
Well, can other people who aren't in the voice chat hear the people on the stream? People in the voice chat?
Yes.
I believe they can.
Okay.
You can like locally mute us all.
What does that mean?
Right click on us and then turn the volume all the way down to 0.
Oh.
Or
What's
just
the point of
press
that?
mute. I don't know.
What's the point of me being in here if I can't hear you?
True. It's just an option.
I have muted you all, I think. It's an interesting idea, but I'm not sure how okay it would be for me to be recording your voices. At least from the AMT's perspective. So I'm just going to leave this voice chat for now. Kevin, don't forget to mute yourself or you'll have an audio loop like the last Range Tree lecture. Oh no, is that happening? Is my voice looping? Or is it just when I'm in the voice channel? Okay, cool. Alright. So persistent segment trees. So far, I guess, you've all been dealing with data structures that let you perform queries and updates, but then usually only let you perform queries on the current state of the data structure. Persistent data structures let you kind of go backwards in time and ask about the state of things in the past. So for example, if you had like an array, you can perform updates to that array by changing values at various indices, but you can't say, all right, I want to know what the value of this position of the array was like, 3 updates ago. You can't do that. But persistent data structures do let you do that. So when it comes to persistence, the key difficult problem you have is whenever you do something like x equals y in your code, like you set x to be the value of y, you now know that x equals y, but the value of x before you set it to y has been lost forever. You can never get that back. And this is obviously very challenging when you want to create a persistent data structure, because you kind of obliterated this information that was in X and you can never get it back. So how could you possibly go back in time? Well, there's kind of 2 ways around that. The first way is whenever you would make some kind of change that would destroy information, you just record that information. So for example, you could say something like, at time t equals 1, so maybe t is like the number of updates or something, x was 3. At time t equals 2, you changed x to be 5. At time t equals 7, you changed x to be 13. And so on. So if you have any kind of data structure that has variables in it, if you keep this kind of diary or this journal, you can now go back in time to whenever you want. All you have to do is, if you want to query the data structure at time, say, t equals 5, all you have to do is whenever you're going through the data structure and accessing variables, you make sure to check your journal and see what the value of the variable was at the given time you're querying it for. So in this way, you can kind of keep track of a diary, I guess, of what all the values of the variables were in your data structure. And this works for pretty much any data structure that you're trying to access. Like as long as it has like some kind of a fixed number of variables that you can kind of keep a journal for, then you can go back in time and figure out what the value of any of those things are. So that's one approach to making a data structure persistent. But there's a second approach. So remember how when you take a variable and you assign it another value, the old information gets destroyed and that really sucks? Well, another way of getting around that is to simply say that you're never ever allowed to change the value of a variable. Like all your values are immutable. So this operation here wouldn't be allowed. You can't do that. Can't do this. That way, because you never ever overwrite the value of a variable, that means that you never ever destroy any information. So in theory, you could go back in time and work out what the value of, work out what the data structure looked like at a given point in time. But of course, saying that is all nice and everything, but how are you supposed to be able to do any kind of update if you're not allowed to ever change the value of anything? And the answer is really simple. If you ever want to change the value of something, you first make a copy of the object, and then you change your new copy. So in this example, if you wanted to say x equals y, you'd instead make a new variable x prime, and you would set that to y. And so now if you want to work out what the value of your data structure was at a previous point in time, you kind of just have to keep track of which variables or objects, I guess, represent the data structure at that given time. So that's all kind of very abstract, but those are kind of like the two main approaches to persistence. One is like you keep a diary of all the changes that you make, and the second is to make sure that you never change anything ever. You just create copies of things whenever you want to make a change. Okay, so how does this apply to range trees? Oh, what did that do? I don't know. Okay. I don't know what this button does. Okay, so let's imagine you have a range tree, and the range tree is like, oh, it's gonna be kind of slow. I apologize. It's gonna be a pretty small range tree. It's only gonna be over 4 elements. But you can kind of imagine, let's say this was like, let's say we're implementing a sum tree. So this is like 2. This is terrible. Oh no. This is like 1. So then this would be 5. This would also be 5. This would be 10. So you can imagine this is what your range tree looks like currently. And when you want to query the value of some range, you just look at the corresponding nodes that cover that range, and you sum them up and you get the answer for the sum of that range. And for now, let's say we're just looking at point updates in the range tree. So maybe you want to change this 2 so it becomes like a 6, in which case this would become like 9, and this would become 14. So traditionally, if you wanted to update this to a 6, you would have to change the value of these 3 nodes. But the problem is that you now can't go backwards in time to before you made that update. So what you do instead is whenever you would make a change to a node, you kind of make a copy of that node. So like a so you kind of make a copy of the node that you're trying to change. So this was now a 6, this was now a 9, and this is now 14. And they connect to each other. So these 3 nodes correspond to these 3 nodes here, these 3 nodes here, and the nodes that didn't change, we still have to refer to them. So you can kind of imagine that instead of just making a copy of all the nodes that we're changing, if we made a copy of just every node, and so we kind of made like a new copy of the range tree, and then we perform the update on this range tree, that's like a very easy way to implement persistence. Whenever you want to go like back to a previous version, you just consult the corresponding copy of the range tree. But that's really slow because the range tree has n nodes. So you can't afford to do that. You can't afford to make all these nodes that you aren't changing. But what you can do is, because you know that all these nodes that you didn't change are the same as the ones in the original range tree, you can just refer to those. So this right child points to there. This right child points to there. And this is a leaf, so it has no children. So this diagram kind of makes things a bit messy and difficult to see, but this node is like the root. Its left subtree would be this node, but we changed it, so it now points to the new node. And the right subtree would be this node, and because it hasn't changed, we can simply just go and refer to that one. And so now, if we want to make a query, the same query, but on the new range tree, the new range tree, how do I want to refer to this? So if we make the same query on the new range tree, but it doesn't change anything. This query doesn't actually refer to any of the nodes that we changed. So that's not a very good example. Okay, let's say that in this range tree, if we wanted, like before we made the update, if we wanted to find the sum of these three things, then we'd need to consult the value of this node and this node. And so in our new range tree, if we want to consult the same three variables, then we'd be referring to this node and this node again. So you can kind of imagine that if you kind of like twist your head a bit, I don't know if there's like a cut and paste, but I don't know how to draw this, but like if we kind of took these three nodes and kind of just moved them over here, like visually, then it would be something like this. And we took this node here and moved it over here visually, you get something like this. You can kind of see how even though we're pointing to a bunch of random nodes in the old range tree, they still kind of form like a proper range tree if you kind of just like squint and visually move things around. So that's the general idea of persistent range trees. Whenever you want to perform any kind of update, instead of changing values of the nodes, you make a copy of every node that you want to change, then you change it, and the children of those nodes are either the new nodes that you created, or if the child hasn't actually changed, you can just refer it back to the old node in your range tree. So does that idea of persistence make sense? Implementation is another question, but this is like the basic idea. Okay, it sounds like people don't have any further questions about this. And I guess if you keep doing updates to this range tree, then the same idea applies. So when you now do an update on this version of the range tree, I don't really want to draw it because it's going to look very messy, but you can kind of imagine that these nodes will never change. These nodes will never change because our like invariant of persistence is to say that whenever we want to change something, we have to make a copy of it first. So that means that all these nodes values are final. And the next update would be another set of nodes that change, and they would have like new values and stuff. And for the nodes that didn't change, they would refer back to the nodes in their original tree. And this might refer to the previous version of the tree, but it can refer to even older versions of the tree if a node hasn't changed in a really long time. Okay, so that's a general idea of persistence. There's not much more to it. So what does this actually look like in implementation? I would imagine that implementation-wise, it's easy to have a memory leak. How can we avoid this? Well, at least in the context of informatics, memory leaks are pretty irrelevant. Because we're okay with just having things like floating around. Because our program is only supposed to live for the amount of time it takes it to process the input and then produce an output, and then it's done. For a long-lived program that's supposed to do like stuff over a period of time, like a server that's supposed to serve web requests or something, then you care about memory leaks because eventually the memory leaks are going to cause you to run out of memory and kill your program. But in informatics, if a memory leak is causing you to run out of memory and kill your program is doing something wrong, is also doing something wrong other than just leaking memory. It's allocating more memory than it's supposed to be able to allocate. The only context where it might matter is if you have a problem that involves trying to do something in limited memory, but That's a very niche application. Yeah, if you're really allocating enough memory to your program, chances are you might just TLE instead. Yeah, I guess if you are creating all these new nodes, you need to make sure that you're keeping track of them somewhere, because if you kind of forget them, you're not going to get them back. Okay, so here is a basic implementation of a persistent range tree. So this is a sum tree. It contains the things that you would expect. It has pointers to the left and right child. I've mentioned this before, but I mention it again. I like having my left and right ranges of every node stored inside the node itself, even though you can calculate it and pass it through the queries and updates. I just find it simpler to do this. And it also has a value that stores the current sum. Exactly, here's one I prepared earlier. Okay, so I guess let's look at the familiar parts first. Here I have the constructor for each node. All it does is it creates two child nodes if this node isn't a leaf. So that just builds up your initial range tree structure. Oh gosh, builds up this initial range tree structure and initializes everything to 0. But you can of course initialize it to whatever you want. I have a function here that just abstracts away the concept of a leaf because I'm really lazy. I'll come back to this function in a second. But let's look at the query. The query doesn't do anything particularly fancy. It does exactly what you'd expect of a range tree. If your query window is outside of the range of this node, you return 0. Otherwise, if it completely dominates this node, then you can just return the value for this node. Otherwise, you have to recurse into your two children and get their sums. Update is where things get a bit more interesting. So the reason that query looks exactly the same as a traditional range tree is because a query doesn't modify anything. Which means that as you're walking through, this version of your range tree, or this version of the range tree, or this version or whatever, you can kind of treat it as if it were a normal non-persistent range tree, because as far as you're concerned, that's exactly what it is. But when we get to the update, there are points where you need to change the value of nodes. So if you change this value from a 2 to a 6, then that means you have to update the sum for this leaf, and then also the sum for all of its parents, all of its ancestors as well. And because the way that we're implementing persistence is we're never allowed to change anything, we have to make a copy, then we have to make a copy. So kind of the key thing we have to do is this update function returns a node. And the reason it returns a node is because if your value if your value would change because of this update, your parent needs to know, because your parent currently points to the old version. And so if you've changed, that means you've had to create a new copy of yourself over here, and your parent now needs to point to you. Now, because your parent, because you've changed, that means that your parent's pointer, instead of pointing to you, now points over here. So even if your parent's value doesn't change, you still need to make a copy, because it's not just this sum variable that we need to make a copy of the node every time we want to change. It's also references to children as well. Because what you don't want to do is, this represents the version of the tree before the update. Oh, this has gotten really messy. Yeah, this is supposed to represent of the version of the tree before the update. So if you take this node and you point it at this new node that you've created because of the update, then suddenly this version of the range tree, it's different now. This value has changed. So you've kind of broken the property that this is supposed to have not been any different from when you had made the update. Like this version of the range tree should not have changed at all between before the update and after the update. Yep. So that's just a long-winded way of saying that because you've made a new node here and you want your parent to point to this new node, you don't have to make a copy of your parent and then make that point to your new node. So that's why we're returning a node pointer here. It's so that we can return a new copy, return the pointer to the new copy of the node, if appropriate. Otherwise, we'll just return a pointer to ourselves because we haven't changed. So the first thing we do is if this update is completely outside of the range of this node, then we know nothing will have changed. So we can just return a pointer to ourselves. That's what this is. By this, I mean this word this. Otherwise, that means that the update partially covers our node. And so that means that there is going to be some change to the value of this node. The value of this node. So that's why we create a new copy of the node. So how do you make a copy of a node? Well, you can just create a new node and then initialize all the variables to be a copy of your current node. But one way you can do it is to use what's called a copy constructor. So if you're familiar with C++, this is a copy constructor. A copy constructor is like a normal constructor, except that it takes in specifically this argument. It has to be a reference to the same type as your class and has to be a const reference. So for those of you who don't know what that means that this constructor takes in a reference to another node, and this constructor is not allowed to change this node at all that's being passed in. That's what const means. And so here I'm just initializing like the new node I'm creating to be a copy of this node they've created. That's why, I'm basically just making a copy of everything here. The reason I've put a colon here and then had this weird funky syntax and then nothing inside the actual function is because I forget exactly what the name of this is, but it's how you set the value of const variables in a constructor. Because this is the only time that you're allowed to set the value of const things. Because once the object has actually been created, technically these const variables can't be changed anymore. But you don't have to do the syntax like this. You can just do it normally like here. So that's what this line is doing. This line is just making a copy of the node. And now we just do completely normal range tree things on this node. So in like your traditional range tree, you would do your usual thing of updating your left child and your right child. And once you updated your left child and your right child, I've split out like the calculation to a new function. You have to recalculate the sum of this current node based on what's happened to your children. But because this is a persistent range tree, we're not allowed to modify our current node. So all these operations we do, instead of doing it on our current node, we just do it on the copy that we created. So this should look pretty familiar, except for the fact that we're doing it on the copy. And then at the end, we just return a pointer to the node that we just created, so that our parents can then set their children's new values appropriately if we've changed ours. Okay, are there any questions on this code? Does this code reasonably make sense? So one thing that someone mentioned at some point is that pointers can be pretty slow. So if you do your persistent range trees like this, you may have to do some optimization on it to make it a little bit faster. And typically when this happens to me, I just end up replacing these node pointers to to indexes into an array of already created nodes. So at the start, I would have something like there would be a vector of nodes. Pointers themselves aren't slow, it's new. Okay, that's not something that I knew. New. Yeah, so at the start I would have like a vector of nodes, like, I don't know, node vector. And whenever I wanted to create a new node, instead of using new, I would have a function that's like, make new and it will just return something like that. Yeah, basically what James is saying here. Like, you pre-allocate your set of nodes, and then whenever you want to make a new node, instead of invoking C++ as new, you just create your own new function, which all it does is sequentially return the next unused node in your vector of nodes. Yeah, you make the array vector or whatever as large as you would ever need it to be for your given problem. So typically for a range tree, you need 4 times as many nodes as the maximum value, plus I think 2 times the log of the number of updates that you have for persistent range trees, because every time you perform an update, you have to make up to log new nodes, or 2 times log new nodes for lazy operations. Yeah, for modern machines like the CMS, it should be fine. But for ORAC is a really old machine, so it might not be so happy having to do like, I don't know, garbage collecty stack manipulation type things. Who knows? Okay, so that's hopefully a reasonable explanation of what a persistent range tree looks like. But that's, so far we've only considered point updates. When we're considering lazy updates, things get a bit more complicated, because with lazy range trees, you have to set like a dirty value and propagate that later. And that can cause some problems, because so far we've maintained that, you know, each of these views of our range trees at a given point in time, their values are supposed to never change once we make them, but lazy propagation breaks that invariant, and you have to be a bit careful with that. Okay. So I guess what does this do? Okay. Let's just create another. Okay. I mean, these nodes have values in them, but what the values are don't really matter. We just need to know which nodes are being changed, so I'm going to leave them all blank. So let's say you now have to deal with a range update. So for example, we're updating this range. So that means traditionally what would happen is this node would change, this node would change, this node would change, and this node would change, and it would be set with a dirty flag, because this entire range is being updated, and because we don't want to propagate to all of its children because that's really slow, we're just going to mark this as to do. There's like a range update here. but we're going to defer the work to doing it till later. So what does that look like in terms of persistence? So we obviously have to make a copy of these 4 nodes because they've changed. This node points here, this node points here, this node points here, and this points to that node over there, and these 2 point to these nodes over here. Can I make that a bit bigger? Okay, so that's all well and good so far, but what happens when we want to do a query, let's say for this range of 1 node in our new range tree? So it would be like, if you could imagine like the node here, we'd be looking at the query for this. So as we're walking down our range tree from here, we'd like go this way, go to here, and because this node has its dirty value set, we need to propagate that down in order for the values of our children to be accurate. So in a traditional range tree, you would kind of just go down into these 2 nodes, and you would push the dirtiness down onto them at this point and update their sum values accordingly. But the problem is with doing that on these 2 nodes here is because that now this particular range tree, it doesn't represent the state of the range tree before that update anymore, because you suddenly change these 2 nodes. So now the values, everything is out of whack. So how do you rectify this? Whenever you need to push down dirty values, because you're changing the value of your 2 children, you simply have to make a copy of those 2 children. So in order to push down this, you would end up making 2 new children. You would push the dirtiness down onto them, and you would update their sum values accordingly. And you would stop referring to the old nodes. So these references back to these nodes disappear. Persistent segment tree beats when? Oh gosh, I don't know if you can do segment tree beats with persistence. I think the answer might be no. At least not full persistence. Maybe partial persistence is possible. Anyway, that's a side tangent and a topic for another day. And by another day, I may mean never. So where was I with this? What on earth is partial persistence? This sounds scary. Oh, that's something that I haven't explained yet. So I forget exactly what the names are, but there's like different forms of persistence. So the form of persistence I'm showing you now is that you keep on performing updates to your data structure, and you want to be able to go back in time at any point and say, what does the data structure look like at this given point in time? But there's a stronger form of persistence than that. So what I've just described, I think, is called partial persistence or linear persistence or something. But there's another version where instead of just being able to go back in time and query the data structure, I want to be able to go back in time and kind of update the structure and fork the universe into 2 new universes. So, God, I'm choking. So you can imagine if you had like a chain of updates here. These are your range tree at different points in time. You might want to say, all right, this is a nice universe, whatever, but I don't really like it. So I'm going to go back in time and look at this version of my data structure and update that one. And here's like a new chain of data structures. And you can like keep going and forking different parts of your data structure to create like a whole bunch of alternative universes. And what? Oh, is there an ad here or something? And so, as someone mentioned, you can kind of think of this as, instead of being like this line of updates that you've got, it's like this massive tree of updates that you have. So even though what I've been showing you here is linear persistence, there's nothing stopping you from taking this idea and just straight up turning it into this idea here. The only difference is that instead of applying the update to the most recent version of the range tree, just apply it to whichever version that you wanted to apply it to. Nothing really changes. So for example, if you wanted to perform another update on this one, you would just make a bunch of new nodes, and these nodes would refer to new nodes that are created, and it might refer back to some of the old nodes in this tree. And so, you know, a given node in this range tree could have several descendants of it refer to it from different universes, depending on how many times you chose to fork this particular node. Okay, that's full persistence, I think. Secretary version control. Yeah, you can kind of imagine it like version control as well. How you can have like, you know, your tree of history and branches and things like that. And so this is all nice and cool, but there's another tangential form of persistence, which isn't really persistence at all. It's called retroactivity. So what you've seen so far is like, you perform updates and queries to your data structure as time goes on. And each update stacks on top of the previous one in some way. But maybe what you want to do is you want to be able to say, all right, you remember that update I did like way back here? Where maybe I said like x equals to 5 or whatever. I don't like that update. I want to change that to x equals 10. Now what happens? And this cascades onto future versions of your data structure as well. So this update, changing it can have effect on what future updates do. This is a lot more difficult to implement than persistence. And if you're interested in this, you can look up retroactive data structures. I think this is all memes, so I'm going to ignore it. Unless there was a legitimate question attached to this nani 37 question marks. Okay. I've gone on a tangent. Now I've forgotten what exactly I was doing. It was lazy range trees or something. Okay, so back to what I was saying before. Remember when we had, we created a copy of these nodes? This node was set to being dirty and it had referred to our old children. Well, when we push down the dirty values, then we stop referring to these old children because we have to make a copy of them in order to be able to push down dirty values to them. Because remember, if you want to change the value of something, you have to make a copy of it. So in this way, before when we said that queries were really nice and simple and they were the same as our old query, as the same as the query in a non-persistent range tree, because we never update anything, so we don't ever need to make copies of anything. That doesn't hold true anymore, because now if we make a query and it touches a node that's dirty, we have to push down those values, which means that we're now updating the children of the current node. Yeah, we're updating the children of the current node, which means that we're doing some modifications, therefore we have to start making copies again. That was a lot closer than I thought I would be. Okay. What have I done? Why can't I leave Vim? Oh, that's why. Okay. So here is an implementation of a lazy persistent range tree. So it looks the same, which is kind of worrying because it's not supposed to be the same. Oh, yes. Oh, I remember now. Okay. So just like a normal range tree, a normal lazy range tree that isn't persistent, we have this clean function. So the idea is every time you enter any range tree function, you always want to make sure the node that you're currently at is clean, so that all the values that you're trying to access are actually correct and the dirtiness has been propagated so that you don't have to worry about it anymore after you invoke this clean function. And this clean function pretty much does what you expect. If the node is dirty, it pushes down the values to its children and updates the children respectively. So I've created a second function here, smear, which does the updating based on the dirtiness. I think it's a bit simpler because we end up invoking this function in a couple of different places. But that's what this is doing. And like I said before, whenever we're pushing down the dirty values to our children, we have to make a copy of them because we're going to change them when we push down the dirty value. And that's why I have on these two lines here, 71 and 72, I make a copy of the nodes before I actually do anything to them. And then I update them. So that's pretty much the only change that you have to implement lazy persistence. Everything else is kind of pretty much the same. You just have to make sure to remember that when you do set the dirty value, you do it on the new copy of the node. Yeah, which is done here. You do it on the new copy instead of doing it on the old copy. Yep, and that's genuinely all there is to persistence. Okay, so does that idea on the whole make sense? Just like how lazy updates and lazy creates on like your standard range tree was like a series of simple modifications to the general idea, persistence is just yet another modification on that idea. And the modification is that every time you want to change something, change the value of something, you have to make a copy of that node first. That's it. That's really all there is to persistent range trees. So if there are no further questions on this, do people feel comfortable with the idea? Would people be able to implement this? I can also share this code if people want it. I didn't do that much testing on it. I did some testing to make sure that it kind of works, but I didn't do much beyond that. So there might be some bugs in here still. Oh yeah, I guess I should point out that when you perform an update, so here, the update function returns a new node, which is the root of the new range tree after you've performed that update. So I've just created a vector of range trees to keep track of all of these updates I'm creating. Yeah, so performing lazy update on a persistent range tree is pretty much the same thing as performing lazy create on a normal range tree. It's just that whenever you would access, instead of building up all the nodes up front, you don't do that. And every time you call any range tree function, you make sure your children exist. If they don't, then you make them. It's pretty much the same. Okay. So I guess the next thing I will do is to go through some applications of persistent range trees. I am feeling a bit dehydrated, so I'm going to go quickly get a drink. In the meantime, I'll let y'all, I don't know, do something.
Hey Angus, what's up? Have you finished preparing the crown decomposition problem yet? Oh, okay, fair enough. So I didn't actually get myself some water. I got myself a glass of milk. You see, I went to the supermarket yesterday and they had like this milk that was really close to expiring. So it was like $1.50 off. So that's a pretty good deal. So I got it. But when I actually went to the cashier to get it checked out, when they scanned it, it was the normal full price for the bottle of milk. And I was like, I mean, it's only $1.50 or whatever, but that's like 40% off or something. So I was like, this milk should be on sale. And the guy was like, oh, I guess so. He couldn't really see like the milk freezer thing from where the checkout was. So he just looked at the expiry date and was like, yeah, that's in 2 days. So I guess he must be right. So he fixed it up. He did his swipe thing and updated the price. And I got me my milk. And on the one hand, I was like, I feel kind of bad for making a fuss over like $1.50. But on the other hand, I saved like, 40% off milk or something. But the downside is now I have to drink like milk instead of water, like pretty much all the time in order to finish it before it expires. But the problem is that I didn't realize at the time that this milk was actually not normal full cream milk. It was light skim milk. And so now I'm kind of like have mixed feelings every time I drink it, because I'm like, I saved money doing this, but also I have to drink skim milk. Okay. Oh gosh. Hopefully you've all had a reasonable break now. So the problem that I wanted to go through is the following. I'll just make a new sheet, why not? Okay. You have n points in the plane. And you have to answer offline queries of the form, given some rectangle, how many points are there inside this rectangle? So for this query, the answer would be 3. For like this query, the answer would be 2. And for this query, the answer would be 0. This is 0. So it's a pretty simple problem. So your first thought is probably like, what the? Why are we looking at a 2D query problem? What does this have to do with persistence? Well, it turns out a really nice application of persistence is being able to do sweep lines that you wouldn't otherwise be able to do. Okay, so let me see, what would be the best way to do this? Okay, let me just draw another example, why not? So here are some points. So the thing is, when you're looking at some rectangle query like this, your first thought is like, that doesn't really seem like something I can do with a range tree. Range trees only kind of let you operate in one dimension. Unless you're talking about 2D range trees, but that's outside the scope of this lecture.
So one thing that you would normally think of doing is to do a sweep of some kind. So you can kind of imagine that you can break down this query for this rectangle, this particular rectangle, into two subqueries. One subquery is like the total number of elements in this entire, the total number of points inside this entire range. And then all you need to do to get the value, the number of points inside this area here, is to subtract off the number of points inside this area right here. Does that make sense? So it's kind of like the same idea as cumulative sum, except in a slightly different dimension. So the reason this is useful is because you've made this arbitrary rectangle query that's kind of annoying, and you've broken it down into queries where you're guaranteed that one side of that query always touches like this arbitrary line that I've drawn here, this like, upper line. And the reason that's useful is because now you can kind of do a sweep. So let's abstract away the problem a bit. Answer a bunch of queries of the form, given this rectangle, given like some rectangle where one side touches this axis, what is the number of points inside that rectangle? So what you can do is you can kind of do a sweep. Let's say you knew what all the queries were up front, so it's an offline problem. Then what you can kind of do is you sort all of these points by their distance from this line here. So this will be the first point, this will be the second point, this will be the third and the fourth and the fifth, and so on. And so what you would do is you would have a sweep line that starts up here and sweeps downwards, and every time you reach a point, as this line sweeps downwards, you add it to a range tree that counts the number of points in a given range. So initially, this range tree would be like all zeros everywhere because there are no points. Just gonna do that. And once the range tree sweeps to here, then this 0 here, that's not a 0 anymore, it becomes a 1. That's now a 1. And similarly, once the line sweeps down to here, so here, this becomes a 1 also. And you get the point. As you sweep down, like this range tree keeps track of the number of points in a given range. And so all you have to do to answer a query at a given point is whenever the sweep line reaches like this lower end of the rectangle, you just do a range query for the total sum of the elements in here. Yeah? And that will tell you precisely the number of elements, the number of points inside this rectangle. And so putting it back in terms of the original problem, if you can answer that query and also this query, then you successfully determined the total number of points in any given subrectangle of the problem, any given like subrectangle of the plane. So what does this have to do with persistence? This like offline sweep, you can just do that with a normal range tree. Well, that's the thing. It's an offline sweep, right? What if the queries that you had were not offline, but they are actually online queries? Well, the problem now is that you can't simply do the sweep anymore because you don't know where the queries are going to be at. So if you do this sweep to get to like to answer some query and you sweep up to like that point, then the next query might be like sometime before it. So you'd have to kind of like undo your sweeping somehow, which you can do in this context, and then answer the query back then. But the next query might be really far along, so you have to like, sweep all the way back down, and you might be jumping backwards and forwards doing all these sweeps, and that can take you a really, really long time. In the worst case, like each time you have to like sweep all the way down, then all the way up, then all the way down, then all the way up. all the way down, all the way up, and so on. Well, that doesn't apply in this case because I'm talking about in the online context, so you can't use Moz anymore. Okay, so not surprisingly, we just talked about a data structure that lets you do exactly what we're looking for. As we go and we sweep through this and do the sweep all the way down to the bottom, if we use a persistent range tree as we sweep along, that means that every single time you do an update, you have a copy of the range tree at that point in the update. So now instead of having to unsweep or resweep, all you have to do to answer a query online is to say, all right, this query corresponds to this particular version of my persistent range tree, so I'm just going to straight up query it there. And using this, you can answer all of your queries, all of your online queries in log n. Does that idea make sense? Okay, I see no questions. So obviously, most problems that you do are usually not online. And I guess if a problem requires you to do it online, maybe it's a module problem or something, then that's one application of persistent range tree. But the more interesting applications are the ones where you're not forced to use persistent range tree because the problem just happens to be online. It's because the range tree or the sweep that you're doing, it's part of a larger, it's just one part of a larger algorithm that's using this range tree, using the queries in this range tree to do something, and you don't know upfront what your algorithm is going to, which queries your algorithm is going to need. That's a very long and abstract way of saying that maybe you have an algorithm that wants to be able to do range queries, but it doesn't know what range queries it wants to do upfront. It might change depending on what the results of previous range queries were. So that's like, I guess, the golden application of persistence, in my opinion. Okay, so let's look at a problem from the set. Kth number. Oops. Kth number. So in this problem, you're given an array. I forget if they're distinct or not, but let's just say they are. Distinct integers. Answer queries of the form, what is the kith largest integer in the range from Li to Ri? And this problem is online. Okay, so as an example, let's say array is something like I regret making them more distinct, but you get the point. So for example, if, oh gosh, no. Okay. If your query was like, for these 4 elements, and ki equals 2, you'd be looking for the second largest element, which in this particular array would be 5. And maybe you had the same query where k equals 4, then the answer would be 2. And in this range, if k equals 1, the answer would be 8. Because you're looking for the largest one. You get the point. Okay, so does that problem make sense? Cool. So your first immediate thought is like, dang, what on earth does this problem have to do with persistent range trees? It kind of looks like a Moz algorithm problem or something, but it's online, so you're really sad. Okay, so what we're going to do is we're going to rephrase the problem slightly. So one way you can kind of think of it is you have an array. Let me actually just get rid of all this stuff first. Yep. Oops. Where's the text button? Yeah. You have an array that's all zeros. And you're gonna perform updates to this array that changes some of these elements to 1. And the order you're gonna change these elements to 1 is in descending order of the value of their corresponding thing. So for example, the first element you would be changing to 1 would be this one, because the value is 9. 8 would be next, 7 would be next, 6 would be next. And you get the idea. As time goes on, you kind of go from changing these things from zeros to ones. And so what does a query look like now in this universe? Oh, I've made the same mistake again. So now, if you're querying for k equals 2 in this range, what you're really asking for is at what point in time does this array of ones and zeros, when is the very first time that this range has exactly 2 ones in it? So that would be when the array looks like something like this, and there are some more ones elsewhere. But the point is, the moment that the second time a 0 changes to a 1 in this range, you know that whatever just changed, that is the second largest number. So in this reformulation of the problem, you're kind of just checking as you change things from 0 to 1, for each range, when is the very first moment that you flip a 0 into a 1 for the kth time? That's how we're seeing the problem now. Okay, so we have this structure here that changes things from 0 to 1. So what if we made this into a persistent data structure that can tell you the number of ones in a given range? And the reason it's persistent is because we want to be able to binary search on the first time this data structure is in such a state where there is exactly k ones in that range. So if we drew out this data structure in full for every query, it would look something like this. This would be a 1. And then the next state, these would be 1s. And in the next state, these would be 1s. And you know, this process repeats for a while, but I'll just keep going until we have enough things. So like that. That's a 1. I guess I'll just go one more for the sake of clarity. So this is what happens as your data structure keeps getting updated. And what you're interested in is, dang it. What you're interested in is this range of things here. So what you can do is you can binary search on which one of these data structures is the first moment we have 2 ones. So in binary search fashion, you might guess that this is the first, you might guess this is the middle moment, and you do the query of your persistent data structure at this point in time, and you can see there is only 1 1, which means that the answer you're looking for is somewhere further down in this range. And so again, you do a query, maybe you do it on this range, you check, wow, there's 2 1s, which means that the answer must be somewhere inside this range, and so on. You narrow things down by binary searching through this data structure. The reason that you needed this data structure to be persistent is that these queries that you're doing, they're such that you don't know when, you don't know which version of the data structure you want to query until you've seen the results of the very previous query. That's how binary search works. You adjust your future query based on what the results of the previous query was. That's why it's necessary to have a persistent range tree here. Otherwise, you could just do your usual offline sweep, and if you knew what all your queries were up front, there would be no reason to do persistence. Okay, so for each of these queries that you do, binary search takes you log time each. Each step in the binary search takes log time, and you have to log the total number of elements in the array operations. So you can answer each of these operations in log squared using persistence. So that's pretty much what this problem is. Now that I mention it, even though I said that this problem was online, I don't think it really helps you if the problem was offline. Because even though you know what all the queries are, you still don't know what the actual queries at which points in time that you're actually going to do up until you do all the binary search things. So it doesn't actually help you yet. So I think that if this was offline, you'd still have to do it this way. You can get order n log n with a different persistent segment tree. I believe it. That's interesting. This is the version of this particular problem that I know. Yes, this takes log squared time because you do a binary search, and each step of the binary search takes log time. Is the order n log n easy to describe? It's a 2-segment tree walk? Oh, okay. Oh, is it the same idea as the other problem? It seems like there is some other discussion going on. Is your binary search for the kth 1-bit set in the tree? Oh yeah, 2D set tree walk. What? I think this might be spoilers for the other problem in the set. Okay, I'll leave it as an exercise to everyone to figure out what the n log n solution is. But I can up the time limit for kth number if this solution doesn't pass. But yeah. So this is kind of like two of the, I guess, standard applications of persistent range trees. Other than like the problem says you have to do it online and you have to be able to go back in time. Okay, so are there any final questions about Are there any final questions about like persistent range trees in general, or I guess persistent data structures? I guess I'll mention now that the idea that we've described so far, even though they're in the context of persistent range trees, there's no reason you can't apply it to any other data structure that has a similar, I guess, structure as a range tree, in that it consists of a bunch of, I guess, objects, in this case nodes, that have a fixed number of variables associated with them. In the case of a range tree node, it's left pointer, right pointer, and sum, and also dirty value, and maybe other things depending on the exact kind of range tree that you're implementing. But there are other things, there are other data structures that fit this description too. For example, union find. So you can also implement a persistent union find using this same idea. A persistent stack is also possible, which I think Angus has already described at some point. And even for data structures that don't fit this kind of nice description, you can still sometimes make them persistent, but you have to do a bit of extra work and do some extra, I guess, algorithmic fiddling. Fully persistent path compression is bad, but partial persistence is okay. But yeah, if you just do it by rank, then everything is fixed. Okay, if there are no further questions, then I think that was the that was what I had planned for this particular lecture. I guess it's a lot shorter than I guess other lectures I've done, but I don't know. That's what is going on. Okay, I will now end the live stream. And by now I mean